and the topic is groundwater flow and age in topography-driven groundwater flow system with geological barriers. My talk is divided into 4 parts. First is why we do it. We know groundwater is quite important for our society. So groundwater renewability is always a topic for our analysis. And we see quite a few experts have written different books and papers, review papers on this topic. And the useful method for understanding groundwater renewability is groundwater age. And we, in the past decades, we know quite a few traces to be used for understanding groundwater systems. And I actually used age traces to estimate groundwater age and with Professor Peter Cook. And these are his studies. Age traces are useful because they are added to the groundwater system by natural processes. So if we can estimate, we can measure these natural traces, we can estimate recharge. You can understand the processes, therefore understand the groundwater renewability. The thing is, estimating or understanding systems from traces is based on some simple assumptions. So in the past, we have got an understanding of flow and age, but in Tóthian flow, it's very complicated. Tóthian flow, which is a topography-driven groundwater flow, was developed. A theory was developed by Tóthian in 1963, and I think people in this lecture understand this. And age has been used to understand Tóthian flow in the past, like O'Malley and Wilson. These are just examples. And myself, and 2 other co-authors to understand the groundwater age in these complicated systems. It's very complicated. So field-based studies have been performed also in the past to understand these processes. And usually they use age traces and also numerical modeling, like combining these 2 different methods to understand the Tóthian flow. And now from a paper by John, I was also a co-author of the paper. We discovered topography-driven groundwater flow from age traces for sampling age traces from multiple depths and interpret them with groundwater modeling. So we know these processes exist from age traces, and we know age traces are quite useful. But in our natural systems, there are also like very complicated stratification, like low permeability. Nanjing can exist in our groundwater systems, and from these examples, these 3 different examples, we see groundwater age can change, can be complicated, and these low permeability from the perspective of flow, we know blocks flow by the name of this term, low permeability blocks groundwater flow. So it increases. It can increase groundwater age, and these are what we understood in the past. In comparison, we know faults not quite well. of course, this is a combination of faults across the globe, and people identify them as different rules, barrier conduit or barrier conduit, and they used a range of methods to determine their fault rules, like hydraulic method, maybe tracer methods, maybe a solid concentration difference, but these are just a simple interpretation from data. So what can we learn from? But what is the exact effect of fault on these systems? And people, like I said, and people use the data, like they measure, for example, on the right-hand side, people measured TDS and chloride concentrations from close to the fault. They can tell the difference between the faults and then identify the role of faults. Also, people did a simple analysis by adding fault to a system, and so basically, from what we understood, we know fault exists, but existing studies haven't really looked at how faults affect flow systems and age. And we know age can be very helpful because we can sample at limited locations and at multiple depths. But can we really detect fault rules with groundwater age when no fault exists or when we don't know fault exists? So these are the motivation of our study. And based on based on literature review, we come up with a method. Because I come up with this framework. We used the hydrogeosphere to do the analysis. It's we started from theoretical analysis because conducting fieldwork is time-consuming. It's also requires a lot of previous analysis. So we would like to start from this theoretical analysis to get some understanding of the process, then plan potential field work afterwards. In this framework, we first select different models and establish baseline models. And in these baseline models, there are no faults, and then we add faults to these baseline models, and then do analysis afterwards. And it is the framework. It is the diagram of the model, and the max changes depending on our requirement. And in our study, we used two different conditions. One is simple, the other is complex. Simple means we have thickness, aquifer thickness of 100 meters, and complex conditions we have different thickness. But basically, we have two different conditions. One simple, one the other is complex. And we apart from the visualization, we also did analysis, calculated the relative age difference. So I will explain this later. It's simply the difference between the model with fault and the model and the baseline model divided by the baseline model. And I'll show you some results. And because it is a theoretical analysis, it's not easy to explain and maybe also hard to understand. And I will try my best to start to do it. And I will start from simple condition. And in this condition, we have we can see from the baseline model, these are the arrows indicate the flow lines, and the color, background color shows the age distribution. So this baseline shows independent flow cells, and also these flow cells from groundwater flow from groundwater flows from recharge to discharge. Basically speaking, they are independent cells, and that's what we understood from the classic Tóthian systems. And when we add faults, to the system. These are two different cases. One is a fault as a barrier, and the other is a fault as a conduit. Basically, fault as a connectivity is very small. Now we see in this case, we see originally there is a cell here. Now it's cut into two. And for the case with fault as a conduit, and we see the flow cell is still complete, but because the fault is in the middle of the cell, now we see the flow is more downwards. Flows deeper into the system. And we can draw a line across these depths. Z equals 25 meters, and compare these different edges. This one shows this one corresponds to this, and this one. So we can see when fault acts as a barrier, groundwater edge increases rapidly right here on the right hand side of the fault, because the flow starts from right, ends on start from right, ends at the left. And then if we look closer to the figure, we see the edge on the left hand side, it becomes younger, and that's what it happens. And for the case with fault connectivity of 20 meters per day, in this case, so we don't see groundwater edge increase, but groundwater edge decrease right here. So of course, we see fault changes the original flow and modifies edge distribution. If we look closer to the area between 8 and 11 kilometers, and we see that when fault acts as a conduit, the edge decreases within the fault zone. On the right hand side, within the fault zone, and the fault zone, there is a sudden change in the curvature of the edge curve along this line, and as hydraulic connectivity increases, the curvature becomes greater. The influential area becomes greater. So we see the wider changes, wider than like compression right here. And we can use the relative edge change to also understand the relative to understand it. And we can see is when we look at these, only a very small area of the for this case, only a very small area has this gamma A greater than 0.5. This means for the case with the fault as a conduit, very small area changed. Very small area changed. The area changed has a edge. Very small area here. The value downstream of the fault is actually here is actually smaller. The green color indicates younger groundwater. This means the flow is faster. The faster means a younger groundwater. When fault acts as a barrier, and we will see a very different and more complicated changes in groundwater age. And in this case, with KF smaller than 0.1 meter per day, we see groundwater age is a younger downstream here, and older. Here is the baseline. The blue is a baseline. But for all other cases with faults added, we see older and younger left, right, and left of the fault. And to come to look at this figure, we know flow comes from right, and because of the resistance of the fault, and flow starts to the groundwater flow moves upwards. But on the right hand side, because of the resistance of flow, it acts as a barrier. So the flow comes from the top, so it receives the recharge from the top, and then discharges to the regional, to the same location. So this gives us two separate flow cells compared to original baseline. And this is the case with the KF smaller than 0.1 meter per day. But we increase the fault hydronic connectivity, we see more complicated phenomenon. For this case, hydronic connectivity is 0.25 meter per day. The existing groundwater flow cannot can start the flow across the fault. Previous one, this is a previous case. This is a 0.1 meter per day. Now we have a KF 0.25 meter per day. We see, look, the change is different. In the previous one, the age here is older, but here is younger. But now at the same location, when K is greater, we only see increase in groundwater age. So this is the through flow of groundwater. If we move upwards, looking at 50 meters, we see the same phenomenon as the previous case, and even shallower location, we see the same phenomenon. But if we look at hydronic connectivity 0.5 meter per day, we see the same phenomenon right here, and then the same phenomenon. So this phenomenon is also through flow. Looking at these pink curve, but here is the phenomenon is the same as the previous case. So it's not easy to understand. We use this schematic diagram to explain our idea, and as we have different hydronic connectivity of the fault, groundwater starts to flow across the fault when KF is 0.25 meter per day, and when KF becomes greater, more area has like through flow. So this is what happens because the KF hydronic connectivity of the fault determines the resistance, the degree of resistance for groundwater flow. And this is the relative age change from from all the cases, with fault as a barrier, we see less green area where when the fault connectivity, hydronic connectivity becomes greater, and we saw we can also see like next area of these red color. This means as we change the hydronic connectivity, the flow becomes closer to the original case. The original case without fault. So I guess this phenomenon or the idea is also easy to understand from this figure. And for the complex case, if we understand the simple case, we can understand the complex case relatively easily. And these are cases I guess we use quite often. We in our study we used 1.5 kilometer and 2 kilometer thickness. The top one has the baseline case and conduit fault case and barrier fault. Bottom one also have all the cases presented. And the fault zones, when the fault acts as a barrier, we don't see much difference between these cases and the baseline case. But when fault acts as a barrier, we see clear a difference here compared to the baseline case. Because the conduit allows faster flow compared to previous case. Now we can also do similar analysis by drawing a line across all cases. Here, this one demonstrates age distribution here and also here, 3 cases. And comparison, we can compare baseline and conduit, right? These green and red curves, they look quite similar. There are 2 phenomena. One is the maximum age increases with distance. That means the regional flow, and there are also like very small areas. And these areas, small age areas, these areas indicate local flow. So when the fault acts as a conduit, we don't see much difference. Previously, we saw difference, right? But the thing is, the aquifer is very thick here, 1.5 meters. But previous case was only 100 meters. If we look closer at the top of 100 meters, we can see the same phenomenon as the previous simple case. For the barrier case, we see the age is increased like rapidly. Now this creates 2 separate regional flow. One is on the right, and the other is on the left. And as we draw more lines, we can see these more obvious. If we look at the 0.5 meter, 500 meter here, we draw the same line. We also see regional flow, but the age here becomes smaller. Here the age becomes smaller, but it becomes the maximum age is quite similar. This means we starts to have less influence of regional flow, and further to the top at 1,000 meters. Now we also see the similar phenomenon, age distribution between baseline and conduit case. But for the barrier case, maximum age is still similar, but the at the top, the influence of regional flow on the influence regional flow right here on this area is negligible. Now we see the age, compare the blue curve in these three different figures. So we see the age. This age is much younger. We can use a relative age difference to also demonstrate the changes. We see the fault affects the development of flow systems, and also we see the age difference, green or this brown color. We see these colors because fault has some impact. And interestingly, in this case, in the conjugate case, we see age increase, and the color, the dark color here indicates increase in age in these two different thickness cases. And this means regional flow still has impact, and due to can allow faster flow. So regional flow can come to this area, has more influence. And for the case with fault acting as a barrier, now similarly we can see changes, but the difference is compared to this color, this color and this color. We see age on the left-hand side, left-hand side of the fault becomes actually younger, but in the case it's older. So that means the barrier fault blocks groundwater flow. So this increase in decrease in age is actually due to local flow or new regional flow in these two separate regional flow. So these are the results, theoretical results from our analysis. I know it's very complicated, but to answer, can we really make use of age to identify fault? We draw this schematic diagram, and we put 4 wheels right here, and these are actual data from our theoretical analysis. So, we can when the fault acting as a barrier, the change is very obvious. In the red color here is we start from this case, the baseline case. The baseline case, we see different inflection points. In well 1, that's inflection point. There's one inflection point, and for well 2, that is very close to the fault, we see 2 inflection points, and for the one on the left-hand side of it, we also see two inflection points, and for the downstream, we see 2 inflection points. And as we understood, the fault affects the flow within this flow system. So we can use the age from upstream of the fault, and we can also use the reason is that we often do multiple sampling at multiple depths. So from multiple sampling, we can identify, 2 inflection points. If we at a location very close to the fault, we can only find 1 inflection point, and we can tell that this fault may act as a barrier. For the downstream, we can also, theoretically speaking, we can also do it, but the influence is very complicated because the flow can can partially occur, flow across the fault can partially occur, but at the upstream of the fault, we see we see a very clear difference between vertical edge distribution. But can we really identify fault as a conduit? From our previous analysis, conduit can still allow groundwater flow, and theoretically speaking, if we, from a big picture of the flow system, we can tell. But the thing is, we can only do like very limited locations. From this figure, we at multiple locations we see vertical distribution of edge are very similar. There's only one well with a clear difference, but it's further downstream. Further away from the fault, more there will be more factors affecting the flow. So for the conduit case, it will be very complicated by simply looking at edge. But if we do it in a different way, like if we know there's a fault, and we tell from vertical distribution of edge, we tell no difference. Like we can still have 2 inflection points, and we can rule out the barrier fault, and we can determine it is a conduit fault, maybe a mixture of a conduit and a barrier. So this is how we can identify fault rules from edge distributions based on our analysis. And this study is very complicated because it has no field sites. But from our analysis, we identified fault can act as conduits and barriers, and they may have different effects on groundwater edge. Based on our analysis, maybe we can still use groundwater edge to identify fault rules, but it requires further field work, and we are very excited if we are very excited to conduct field work in the future, and also to continue our topography-driven groundwater flow study. And the talk is purely based on this study published in 2025 in Journal of Hydrology, and we also connected 2 other studies, one published in Geology, and the other also published in Journal of Hydrology. These are also about topography-driven groundwater flow, but I may talk about it later. That's all my talk. Thank you so much. I hope this will create some discussion.